what would you guess that this class would be about? You have any clue? It's okay if you don't. I'm kind of curious.
No. Probably like graphs or like vectors.
Okay, I heard vectors, and then what else did you say?
I don't like graphs.
Graphs? Okay, yeah. We've got a lot of graphs in Calculus 1 and 2, and we'll have more graphs in Calculus 3. So what did you guys do in Calculus 1? You remember?
Derivatives.
Derivatives? Integrals? Okay, good. And what did you do in Calculus 2?
More integrals.
More integrals. That's basically it. And then what else did you do in Calculus 2 that seemed maybe separate from everything else?
Or work.
Okay, yes. What else?
Sequence and series.
Yeah, I'm thinking of series. So I don't know how much you did with polar coordinates or how much you did with sequences and series. Series, I don't know if you guys made the connection in your Calculus 2 class. Series are used to solve really complicated integrals. So it does fit in with Calculus 2. It is integrals. Here in this class, we're going to take what you've done in Calculus 1 and Calculus 2 and use it to do stuff in more dimensions, basically. That's a rough way to say it, or at least the first idea that you should probably have. So you've done derivatives and integrals. We're going to start doing that in 3 dimensions and more dimensions. So that would be nice to be able to calculate things like center of mass, moments of inertia. We will also develop some tools that are really useful for talking about things like electricity and magnetism. So the stuff that you've already learned when we bump it up to 3 dimensions can handle classical mechanics. The new stuff that we're going to learn is going to be able to handle fluid flows, electricity and magnetism, and some heat transfer. So it will be very complex stuff. This is a very challenging class, but you're welcome. It is intuitively nice in the sense that something like pre-calculus throws together a whole bunch of topics that don't fit together very well. Here, like, we build up stuff in Unit 1, we build up some more stuff in Unit 2, we combine them in Unit 3 to handle really complex physics. The all-star for this class is what somebody already mentioned, it's vectors. So vectors are pretty simple. You've probably already studied them in some context. Does anybody want to try to give me a definition of a vector from somewhere that you've studied it before?
A one-column matrix.
Okay, good. One-column matrix. So if we're in 3 dimensions, for example, we can write it like this. X, Y, Z. That gives, well, what did that give for you when you studied it as a one-column matrix? Are you thinking of like computer science or linear algebra? Okay, okay. So this probably represented like a geometric vector for you. Whereas in computer science, you might use something like this just as to represent a list of stuff. Any other definitions of what you heard for vector?
In physics, it's something that has magnitude and direction.
Okay, something that has magnitude and a direction. Good. So that's basically how we're going to think about it in here. Something that has magnitude and direction. So we can represent that with an arrow. Let's put this in 3 dimensions. So this will be an x-axis and a y-axis. That forms a plane, a flat plane that's like the floor of this room. So if you can imagine the x-axis coming sort of out at us, the y-axis going that way, creates a floor, and then we'll have another variable that we'll call z that gives us a vertical component. So this top half is like this corner of the room, basically, or that corner. Then if the vector goes from the origin to the point x, y, z, we can represent it like this. Or in this class, the way that we'll usually represent it is like this, with It's a simple thing, but it's extremely useful for communicating the ideas and organizing the ideas that we're going to be talking about this semester. If it's something that just has a length and a direction, then if I draw it over here, it's still the same thing. If it has the same, if I drew it where it had the same direction and the same length, then it is equal to this, even if I put it over here. It has the same length and the same direction, it's the same vector. So if I take this point and this point, and I subtract these coordinates from these coordinates to get these coordinates, then it will be the same vector. A couple of ways that this thing will be useful is in telling us how to calculate work and torque. So let's say that we have an object and a force is applied to it. And if this thing moves, let's see, if the force is going in the same direction as the object is moving, you guys know the equation for work?
So distance times the force.
Okay, good. It's force times distance. Maybe you represent it as just F times V. That's if the force is moving in the same direction as the displacement. What do we do if the force is moving in a different direction?
The direction of the angle cosine.
Okay, good. This angle comes into account, and we'll need to use the cosine of that because the cosine of the angle is this side divided by the hypotenuse. The hypotenuse is the force itself, the magnitude of the force. And so if you use that, then you get, what is it? F cosine theta times the displacement. So what you're basically doing is you're calculating this length. This is F times cosine theta, because cosine theta is this length, I'll call it X, over this length, which is the magnitude of the force. But there's a product that we'll talk about that gives us this immediately. And I'm going to take two vectors, so I'm going to represent these in their vector form like this. And I have a special way of multiplying these two vectors so that it automatically takes into account this stuff, this angle, and gives me the work. So we'll call that the dot product. I'll show you how to calculate it soon. The other thing that I wanted to mention is torque. So let's say we've got a wrench being applied to a bolt. And let's say force is applied to this, maybe like that. So here's a force vector F, and then we've got a vector here that I'll call R. It's usually called something like the arm. If you've calculated this before, you may remember that you just take the component of F that's perpendicular to the arm, because if you think about it, that's all that matters. If I'm pushing down a wrench, the force going perpendicular to it is the only force that will cause torque. If I give it force this way, it's not going to induce any torque. And one of the main reasons that vectors are so useful, I think, is because you can break this thing up into components going in two perpendicular directions like this. If I know how to express the blue component and the red component, if I just add their their coordinates together. If I represent them both like this, and I just add the x's together, the y's together, the z's together, then it gives me the force. So I think that's why these are extremely useful for communicating about forces. If you find this length, then you multiply that times the length of r, and that gives you the torque. I'm going to represent torque as a vector. So here it's going into the wall. It has a magnitude and a direction. The direction is into the wall. The magnitude is the magnitude of torque, the way it's defined in physics. So to get this length, you use sine. So I'm going to say the magnitude of this. I'll use vertical bars like absolute value to say this is the length of the vector. The length of that is going to be f times sine theta times r, where r is the length of this guy. So the length of this is very similar to this other product, but this one is a vector. It also gives me a direction. The way we'll represent this product, so this torque is going to be r cross f for us. So we call this one the dot product, call this one the cross product. This is also useful for other things. One thing it's useful for is describing if you've got a charged particle moving through a magnetic field. This cross product is useful for describing the force generated by, the magnetic force generated by that particle, the charged particle. All right, I want to mention a couple of other things that these products do for us before we look at the syllabus. So another thing that this cross product will do for us is it will allow us to describe planes. So if I want to describe a flat plane in space, this is the 3D analog of a line in 2 dimensions. And lines are really easy to describe. You just need a point on the line and a slope. And you can describe the line. So this should be pretty easy to describe. But in a little bit, I'll give you a chance to think about how to describe it. Right now, I'm just going to tell you that this cross product is going to give us a tool that will allow us to describe that nicely. We'll also talk about how to calculate that cross product. I want to point out, before we get to the calculation part, that the fact that it takes into account this angle in both of these products should tell you that this calculation might be complicated. Because it's telling us something, it's like encoding some really useful information. We may not even know what the angle is, and we can still calculate the torque or the work. All right, last, let's say that we've got some kind of fluid flow. And I'm going to draw a wavy surface here. So we're in the context of some kind of fluid flowing. Or we could be in the context of a force field, some type of force field. So we would represent this with arrows. The length of the arrows would represent the magnitude or the velocity of the flow or the force. And then, of course, the direction represents the direction that it's moving. What we'll be able to calculate toward the end of the semester is how much stuff is moving through the surface. So we've got some curved surface, and we've got this field. How much stuff is being pushed through? For example, if this is a flow, how much mass is flowing through that surface per unit time? This is called a flux, and there's there's an electric flux, there's a magnetic flux. Those are measuring something. It's not mass, but it's something. It's some kind of measurement of how much stuff is moving through the surface. And this dot product is actually what allows us to calculate something like this. So, if the displacement, so if the direction is a unit vector, meaning it only has length 1, if this has length 1, then this d is 1. And the f cosine theta in that case is just telling us how much of the vector is moving in a certain direction. So the vector that we're choosing here, d, would just represent some direction for us. Over here, it would represent the direction going perpendicular to the surface. So something like that. If I choose this to only have length 1, and I calculate this dot product, then it tells me exactly how much of the vector f is pointing outside or perpendicular to the surface. So if you've got your f moving like this, better. If you got f moving like this, oh no, I forgot. I chose d to be unit vector, so let me draw f, not even close to the length of d. There's a component of this that's going directly out through the surface, and then there's a component of it that's moving parallel to the surface at that point. The component that's moving parallel to the surface at that point basically doesn't send anything out of the surface, so we can use the dot product to focus on how much of this is moving out through the surface.